Dear students, welcome back to this week's lectures. And we have reached section 4.4.3, in which we will discuss some examples that are often used in financial mathematics. We will see some properties that are representative for price processes. And we will start with a model for the price of a stock price development. And after that, we will discuss a model that represents interest rates. So we will analyze these processes and see their properties, see a solution. But the first necessary ingredients are, of course, a Brownian motion. We have given a Brownian motion, Wt, t greater or equal to 0, and it comes with a filtration script ft, t greater or equal to 0. Then we define two nice adapted processes, alpha t, t greater or equal to 0, and sigma t, t greater or equal to 0. They are assumed to be nicely adapted processes, and nice in the sense that all the properties to define a stochastic integral and a regular integral are satisfied, so they exist, and they therefore have all the properties we need. And based on those, alpha and sigma, we define the Ito process. And our Ito process is called X here, and it looks as follows. X of t is the integral from 0 to t, sigma u dwu, plus the integral from 0 to t, alpha u minus 1/2 sigma square u du. So we see here the stochastic integral with respect to the Brownian increments, and here we see a regular integral, alpha u minus 1/2 sigma square u du. And that is an Ito process. And we have seen last time that this falls under the definition of an Ito process. See sigma u here and minus 1/2 sigma square u here, and we will later see why we have defined it in such a way. Now in differential notation, of course, this is written like this. dx is sigma t dwt plus alpha t minus 1/2 sigma square t dt. So it's better readable like this. All right, so this is our point of departure. And now we consider that price process we just discussed, and that price process is S, stock price, S, t greater or equal to 0, and that is now defined as of t is equal to S0 e to the power xt, where that xt is written like here. So S0 is something like the stock value, the stock price at t equals 0. At the time now, for example, something which is known. And then e to the power xt, where xt is given by this, that can be seen as a possible development of the stock price in the future, t greater or equal to 0. And suppose that t0 equals 0 is now. Well, if the stock price now is positive, then you see that it will stay positive in the future because it's an exponential function. And that is very convenient. That is one of the properties that we would like to have. And then apparently we have e to the power this integral plus this integral. So if we write it out, then we get indeed, we substitute for x, we substitute this process over here. We get that is S0 e to the power, the integral from 0 to t, sigma u dwu, plus the integral from 0 to t, alpha u minus 1/2 sigma square u du. So this is our price process, and we would like to understand the properties for it. So in particular, what we would like to express st, t greater or equal to 0 as an Ito process. And for that, we will use Ito Dublin's formula. And we will use for our f in the Ito Dublin formula of an f which only depends on x and not on t, and we will choose the one which makes sense from the definition on the previous slide. F of x is S0 e to the x. Yeah, we know for this function all the derivatives exist. So all the properties that we need are satisfied. We have no problem. All derivatives exist and are continuous. Well, we want to use Ito Dublin's formula, also sometimes called Ito's lemma. And if you don't remember that, please look back at the previous videos, because that is a machinery that we will be often using here. The first derivative of this function, of course, is not too difficult. That is equal to S0 e to the x, and it's the same function for the second derivative. So we can immediately express the Ito process with the help of the Ito Dublin formula, where we say S0 is equal to S0 e to the x, and that is our definition of our function f, which depends on x, x being x of t, and that is our function f at x0 plus the integral. So here we get the fx term dx, so that is the integral from 0 to t s0 e to the xu dxu. And here we have the second derivative, the 1/2 from the Ito Dublin formula, plus 1/2 the integral from 0 to t, f double the second derivative, fxx, s0 e to the xu dxu dxu. So this is the standard use of the Ito Dublin formula, and now we can substitute the individual parts that we know from the previous slide. So let's look back at the previous slide. We know dx is sigma t dwt plus alpha t minus 1/2 sigma squared dt. We know that, and we can substitute that. And for such a process, we have also seen dxt dxt, right? So that we will also be using. So we will substitute for dx. Here, we substitute the differential form, and for dxu, dxu, we will also substitute the form that we have learned. So substituting for dx sigma u dwu plus alpha u minus 1/2 sigma square u. So that is d du. So that is the definition of dx. dxu is written here plus here, this part plus this part with a minus sign. So we end up with st is equal to su. Remember that for x equal to 0, e to the 0 is 1. So this is just s0 plus the integral su. Because remember that this part here is just su. So we can substitute su, and the same here. This is su. So we can use that. And therefore we can write st is s0 plus the integral from 0 to t su. And then we substitute for dx sigma u dwu here, plus the integral from 0 to t su times the other part, alpha u minus 1/2 sigma square u du. And then again, remember that dxu, this differential form, that is in fact equal to sigma square u du. We have also seen that in the previous video. So we add to this part here plus 1/2 the integral from 0 to t su sigma square u du. So these are the parts that we get when we substitute this, when we try to express this as an Ito process, and we also see that some term cancels out. The term here, SU 1/2 sigma square u du with a minus sign is here with a plus sign, so they cancel each other out, this part and this part. So what remains is the following: S of t is equal to S of 0 plus the integral from 0 to t, SU sigma u dw u plus the integral from 0 to t, SU alpha u du. So we see this part, we see this part, and we see this part reappearing. And that is indeed an Ito process, right? And we can also write this in differential form. So first of all, this is an Ito process. And in differential form, this one looks, let's look again. This one then goes to the right-hand side. We get something like du is SU sigma u dwu plus SU alpha u du, and for the u we can substitute a t, and we end up with the Ito process st, t greater or equal to 0, and it satisfies this equation. dst is S is equal to st sigma t dwt plus st alpha t dt. And such an equation describing the development of the process S, is a stochastic differential equation. That's an SDE. Now, looking in reverse, suppose what we can say is that when we are dealing with this stochastic differential equation, then the solution, in fact, of this is our point of departure. The solution will be this one, right? So we went from here to the SDE, but looking in reverse, we can say the solution to the SDE, is in fact, so the solution to this stochastic differential equation, the solution is given by this process here. St is equal to S0 e to the power integral from 0 to t sigma u dwu plus the integral from 0 to t alpha u minus 1/2 sigma square u du. So the difference being, of course, that in this form, this is a solution, an explicit form, because ST is not in the right-hand side, not explicitly found in the right-hand side anymore. Here we have it, of course, right? That is the SDE form. And then this is the solution. It says ST is equal to S0 times this development with some random increment here, the Brownian increment. So looking in reverse, we know the solution to this stochastic differential equation, and that is this form here. Now we can look at, we will do some remarks. We can look at some simplifications. When alpha and sigma are constants, when here is just a sigma, and here is just an alpha, and here is just a sigma square, then we can simplify this. So the integral from 0 to t of sigma dw is just sigma wt, right? W0 is equal to 0. That is just sigma wt. And here, when these are constants, this is, of course, a regular integral, an integral from 0 to t of some constant alpha minus 1/2 sigma square du is, in fact, alpha minus 1/2 sigma square times t. Right? That is the solution. So we have an explicit solution if these sigma and alpha processes are just constants. When they are constants, that gives us the SDE dst is equal to st times sigma dwt plus st times alpha dwt. And we, in finance, we often write dst is alpha st dt plus sigma st dwt. This is how we often write it. So a part which has only a dt term, and we call that, in fact, often we call that a drift term. And here we have a part with a Brownian increment, and we call that a diffusion term. But that'll follow later. However, what I just mentioned, if we have sigma and alpha constants, so when we have the stochastic differential equation as follows, dst is equal to sigma times st dwt plus alpha times st dt, then the solution is the so-called geometric Brownian motion, and that I've just shown you on the previous slide when we went back. The solution being st is equal to s0 e to the power sigma wt, the d will cancel out when I post the slides, sigma wt plus alpha minus 1/2 sigma squared times t. So again, we know the solution. It's e to the power this expression, and the expression we have also seen before in some previous lectures. So e to the power sigma wt plus alpha minus 1/2 sigma squared times t, and that is called geometric Brownian motion. Yeah. So a model for stock prices is this geometric Brownian motion. When alpha and sigma would be constants, then this is the solution. Well, if you think about it, this is a possible price process. We are at time t0, and we say something about the price development in the future. And so this sigma says something about the uncertainty in the future, and this alpha says something about the growth rate of the stock in the future. And that's not easy to say at time t0, right? If something happens, they change drastically, but that is the setting. The setting is basically when this is my timeline, and this is t0, and this is my stock value now. Then we say something about the uncertainty in the future in this term, and we say something about the growth rate of the stock in the future by this term. And then we get this. But of course, because it's an uncertain process, if we generate it, we have random numbers here, and they are drawn from this distribution. So the next possible path would be different, and the next one would be different as well, etc. Only we know something about the density here, the distribution here, or we know something about the mean and the variance of such a process. This is the setting. We are at t0, we have s0, time runs, and this is a mathematical model for the stock price behavior. Now, a second remark, when sigma is constant and alpha is equal to 0, then when alpha is equal to 0, we go back. No, we don't need to go back. We can see that here when alpha is equal to 0, then this term will cancel out, and we are left with this process. dst is sigma times st dwt. Yeah, that process over here. And we have seen that before. Yeah, we have examined this process in an earlier stage. Of course, then we also know the solution. Alpha drops out here. Alpha is equal to 0. So we get the solution st is s0 e to the power sigma wt minus 1/2 sigma squared times t. And we have seen that solution before. We have examined that before, and we have so again, if we see the solution of the SDE, and the SDE is just written in integral form as follows. This is nothing but ST is S0 plus the integral from 0 to t sigma SU dWu. And the solution is then given by this expression. St is equal to S0 e to the power sigma Wt minus 1/2 sigma squared times t. And we know for this one, we have seen that in a previous one, we have shown that this is a martingale with respect to the filtration of the Brownian motion, script ft t greater equal to 0. So in the case that alpha is equal to 0, we are even dealing with a martingale. All right. Now, we want to discuss a theorem. We want to discuss the Ito integral of a deterministic process. So now we say, let's assume a deterministic process delta. So delta, our delta t, t greater equal to 0, that is not a random process here. It's deterministic. So it is adapted. It's adapted, but it's non-random. Yeah, so it's independent of an event, little omega, in the event space, big omega. It only depends on t. Yeah, so when we are dealing with a process delta t, t greater equal to 0, which is deterministic, we know more. So then we know that that is our theorem. Then the integral it, the integral from 0 to t of delta u dwu, that is in fact normally distributed. So we can prove, and that is a non-trivial or a proof which is a little bit involved, so it takes some time of this lecture. We can prove that it, the integral from 0 to t of a deterministic function delta u dwu, is normally distributed with mean 0 and with a variance equal to the integral from 0 to t delta square u du. Yeah, and this mean 0 and the variance equal to this value, we would know already. Yeah, we know that from the definition of such an integral, also for a non-random process, right? We know that this is an Ito integral, it has mean 0, and it has this variance. We have seen that in previous slides. But now, moreover, we know that it is normally distributed. So IT, in this case, is the integral from 0 to t of delta u dwu, that is in fact distributed normally with mean 0 and variance, the integral from 0 to t delta square u du. And we would like to prove that with the tools that we have defined so far. Let's go, right? The proof. So recall, first of all, that IT is a martingale. Yeah, IT t greater equal to 0 is a martingale. That's that is already seen in a previous lecture. So therefore, also in expectation, the expected value of IT is equal to the expected value of I at 0, and that is equal to 0. That is already our mean value is 0. Secondly, again, by the Ito isometry, we have that the variance of IT, that is equal to the second moment, so the expected value of I square of t, and that is equal to the integral of the expected value of the integral from 0 to t delta square u du. And now recall that delta is a deterministic function. So this is the expected value of just a deterministic function, and that is just the function itself. Because delta u is deterministic, this expected value is just the value itself, the integral from 0 to t of delta square u du. So these are the two terms that are written here. The mean 0 and the variance equal to this term here. That is true for by the fact that IT is a martingale. Now we need to show that IT is normally distributed with that mean and that variance. And we will show that in a special way. We will show that using the moment generating function. By means of the moment generating function is maybe the easiest way to show this. And remember, if we can show that the moment generating function, so E, the expectation of e to the power s I t, when that is equal to e to the power 1/2 s square, the integral from 0 to t delta square u du, when we are able to show that, we have shown that IT is normally distributed with this mean and this variance. If X is normally distributed with mean 0 and variance sigma square, then the moment generating function is given and defined as the expected value of e to the ux is equal to e to the power 1/2 u squared sigma squared. So that is a known fact. When x is normally distributed, then the moment generating function is given by this expression, when this is the mean and this is the variance. So in our case, when we can show that for u we have s here, for x we have I, when we can show that in expectation e to the power s I t is equal to e to the power 1/2 s squared times this variance, the integral from 0 to t delta square u du, when we are able to show that, then we have shown that our integral is normally distributed. And to do that, we do a trick. Yeah, we take the the right-hand side, we bring it to the left-hand side in this expression. So it is an equivalent expression. We take the right-hand side to the left-hand side. This expectation minus this should be equal to 0 in that case. And of course, this is, remember again, that delta is a deterministic function. So this is a deterministic function. It can be taken under the expectation operator. So we can say, okay, in expectation, e to the power sit minus 1/2 the integral from 0 to t s squared delta square u du, that should be equal to 1. When these two are identical, when these two are identical, then e to the 0 is equal to 1. Yeah, recall again, we can take this expression under the expectation sign because delta is a deterministic function. So that is what we want to do, and for that we define x as this exponent here. So x is defined as s times it minus 1/2 the integral from 0 to t s square delta square u du. And we would like to examine that. We would like to examine this expression here, and we will substitute for it its definition. So therefore this is the integral from 0 to t of s times delta u dw u, right? That is the first expression here is equal to that part, and the other part we just copy, minus 1/2 the integral from 0 to t s squared delta square u du. And now if we look at it here, we see that this is an Ito process. We have a dw term here, we have a du term here, and so this is an Ito process that we're dealing with. And with this x version, we can look at st, which is e to the power xt, and that is then e to the power the integral from 0 to t s times delta u dwu minus the integral from 0 to t 1/2 s squared delta square u du. So we consider this process. And if we look at this process, so if we look at this process, we see that we are in fact dealing with the case, and we are dealing with an Ito process with a case where this is like a sigma u, And then here we have, in fact, sigma square u, right? So this is a process that we have seen before, right? So the process that we have just been dealing with, in fact, it's e to the power, the integral from 0 to t, sigma u dwu minus 1/2 the integral from 0 to t, sigma square u times du. So this is the case, the geometric Brownian motion case, where sigma t is explicitly written as s times delta t, and alpha is equal to 0. That was exactly the expression, if we look back. And we know a lot for this, right? So we know then that this S is an Ito process. So when alpha is equal to 0 and sigma has a specific form, then we know that this is an Ito process. The Ito process with the general sigma being written as dst is st times sigma t dwt, and written in integral form. So this is the SDE formulation. This is the Ito process formulation. ST is equal to S0 plus the integral from 0 to t SU sigma u dwu, and that is an Ito integral. And for those, we know that this is a martingale, right? We know that this is a martingale, and we will benefit from this here. Because this being a martingale tells us that in expectation, the expected value of ST is the expected value of S0. And the expected value of S0, if we look back to the definition of this, so here we have the definition here. ST is e to the xt. And that is given by this expression, e to the power, the integral from 0 to t minus this. And S0, in fact, if we look at this, S0 is equal to 1 in this case, right? So by having this Ito integral being a martingale, of course, then it says that in expectation, the expected value of ST is equal to 1. In other words, the expected value of ST is equal to S0. That is 1 because of the previous slide. And that tells us then, if we substitute the definition, go back again, we substitute the definition, then this is what we have called ST, e to the xt. And xt, remember, we made for xt this combination. So we are looking at this expression. We are looking at this expression. And now we have shown that this is equal to 1. So it's S0, it's equal to 1. And it, in fact, is the expected value of ST. And that is e to the power SIT minus 1/2 the integral from 0 to t s square delta square u du. And that's equal to 1. And this is exactly what we wanted. So this is exactly as required. So what we have shown now is that, in fact, the expected value of e to the SIT, the moment generating function, is indeed e to the power 1/2 s square integral from 0 to t delta square u du. And that was the definition when the moment generating function is defined like this. That is the definition for the process being normally distributed. Now we have already seen what the mean and what the variance was, so we can conclude that indeed the integral IT in this case is normally distributed with mean 0 and variance, the integral from 0 to t delta square u du. And that is, in fact, the basis of our theorem. That is what we just mentioned. So the theorem, the Ito integral of a deterministic process, is in fact normally distributed with mean 0 and variance equal to this integral from 0 to t delta square u du. And we have shown that by means of the moment generating function. There we are, right? So that is very nice. We have shown that. That's an interesting step. And now we look at another model. So a second example in financial mathematics is a model for the interest rate. And that is the so-called Fasi-Check interest rate model. So now we will look at an interest rate process. We name it capital R, RT, t greater equal to 0, and it is a stochastic process. So also for the interest rate, we will model it as a process with a random part. So we don't know the interest rate for sure. We may know it for the short term, but in the real long term, and think of pension funds, they have assets and liabilities that run for more than 20, 30, 40, 50 years. In that case, we don't know the interest rate deterministically, and we need to model it as a stochastic process. Now, the stochastic process that we will, so the fundamental stochastic process for interest rates is this Fasi-Check interest rate model. And again, we have two forms, the SDE form and the Ito process form. We start with the Ito process form. It says R at t, so the interest rate at some point t in the future, is modeled, mathematically modeled as R0, the interest rate now, plus a strange term, the integral from 0 to t, alpha minus beta Ru du, plus the integral from 0 to t sigma dwu. And this is, of course, a little artificial because sigma is a constant, and this is just sigma times wt. So we have three constants in this form, alpha, beta, and sigma. They're all positive. And of course, then how do you get to these constants? You calibrate it to the real world. You look at the real world values for interest rates in 1 year, in 5 year, and 10-year bonds. So interest rate derivatives. We can extract them from the market, and based on these market prices, we can fit our mathematical model, and we can give numbers to alpha, beta, and sigma. Later, we will look in some more detail at this specific form. So this form, again, the interest rate at time t in the future is the interest rate now, plus an integral of again, a term with a du term, and another term with a Brownian increment. Now, we also have an SDE formulation for this, of course, and that is then taking this to the right-hand side, looking at the D formulation, the change in interest rate, DRT, that is then equal to the term here, alpha minus beta RT dt, plus the term here, plus sigma dwt. This is the interest rate formulation, the Fasi-Check SDE. So it has some growth term, again, a dt term, a dw term. So it is a process as we have seen them before, right? Now, still, we would like to get to a solution of this. And again, remember, a solution means that RT is at the left-hand side, and there's no RU or anything like that in the right-hand side. R0, of course, yes, but there's not a term like this. We would like to get to an explicit solution for this SDE. So the aim is to find a closed form solution for RT. How to get there? Well, again, it is Ito Dublin that we will be using, and it is not so easy to immediately find that solution. So we will do it a little differently here. We will just have a claim. We will say this is the solution. This expression here which looks a bit involved, that is the solution. See that I've given the Ito process form, I've given it a name, I call it equation 1. And now the solution to that Ito process is given also a name, equation number 2. So we have RT is e to the power minus beta t R0 plus alpha over beta 1 minus e to the power minus beta t plus sigma e to the power minus beta t, the integral from 0 to t, e to the power beta s dws. That is then the solution. Equation 2 is the solution for the Ito process in equation 1. And we can find that solution, and we will do that with the help of Ito Duplin's formula. And notice that indeed here, this is a solution as the right-hand side does not contain an RT term. So what we will do is we will be using this, and we will get back to the equation. So the claim is that this is the solution. The claim is that 2 satisfies 1, and that claim is proved by showing that 2 satisfies 1 on the basis of the Ito Duplin formula. So we need an f of t and x. And here you see a t term. This is a term which purely depends on t. So here you see a term which purely depends on t. And here we see something with a dw term here and a time term. So there will be a part of the function which depends on both time and on some x. So we will be using the following form: f, which depends on t and x. We will see it as based on this specific formulation in equation number 2. We will see it as a term like this. So this is the term which depends on time, e to the power minus beta t R0 plus alpha over beta 1 minus e to the power minus bt. That is our function which purely depends on time, plus sigma e to the power minus beta t times x. Yeah. So here we see motivated by 2 means this part we see here appearing here, and this part here we see as sigma e to the power minus beta t times x. Yeah, so x in this case, xt, is then written as the integral from 0 to t e to the power beta s dws. And if we look carefully at this xt term, we see that it is an Ito integral of a deterministic process, because the deterministic process, delta, we use delta for the deterministic process up until now, that is in this case e to the power beta t. Yes? So again, we can use the theory that we have just learned in order to do this. So again, we come with a claim. We want to show that 2 is indeed the solution of 1. And therefore, we write 2. We write equation 2 in the form that we can use Ito Duplin's formula. We have an f, which depends on t and x, motivated by 2, written as follows. And now we will use the Ito Duplin formula. So we need the first derivative and the second derivative with respect to space x, space variable x, and the first derivative with respect to time variable t. Again, because this is an Ito integral with a deterministic process, we know it is normally distributed, and we know its mean and its variance, right? So by the previous theorem, we know that x is normally distributed with mean 0, and the variance, the integral from 0 to t, e to the power 2 beta s ds. And of course, this is just a deterministic integral. We know this one, right? It's 1 over 2 beta times e to the power 2 beta t minus 1. So x is normally distributed with mean 0 and variance 1 over 2 beta times e to the power 2 beta t minus 1. Now, Ito Dublin. Yeah, so RT is f of t and xt. Yeah, and we are seeking this form. RT is f of t and xt. As mentioned, we need the first derivative with respect to time. Let's look at f again. F, the first derivative with respect to time, the derivative here, here we see something, and here we see something appearing, and the derivative with respect to x will be here, and the second derivative with respect to x will be 0, as you see. So let's look again. The derivative with respect to time of the previous expression is minus beta e to the power minus beta t r0 plus alpha e to the power minus beta t minus sigma beta e to the power minus beta t times x. That is the first derivative with respect to t. Please check it yourself. And what we do now, we will do a trick in order to make this a better usable form. So we add and subtract alpha times beta over beta. We add and subtract alpha times beta over beta in order to make this a little bit nicer formulation. So when we do that, we can take a beta out, minus beta outside of brackets, and what remains is this part, minus of e to the power minus beta t r0. Taking a beta out gives us this expression here. So that is alpha over beta minus e to the power minus beta t. Now the minus term here, that is here, in fact. And this part here, the beta is taken out, so, and the minus as well. So plus sigma e to the power minus beta t times x. And the plus term here that remains, and that is in fact plus alpha. Right? So the minus form here enters here. Beta and beta, they compensate each other. And the plus form is here. And by this, we can take beta out of these square brackets here. And why do we do that? We do that because these first terms, they have a convenient form. These first terms, they are in fact f. Yeah, they are in these terms here are f. So it's alpha minus beta times f. Alpha minus beta times f. This is the function f that we have in the square brackets. So that is convenient. We will be using that later on, the fact that there's a convenient expression here. The first derivative with respect to x will give us only the last part. So that is sigma e to the power minus beta t. And there's no x term here. So the second derivative with respect to x is equal to 0. And then we have all the ingredients. So the first derivative with respect to t, the first derivative with respect to x, and the second derivative with respect to x to actually apply the Ito-Dublin formula. So we do that for r. We say r is equal to f, which depends on t and xt. And Ito-Dublin tells us that this is f at 0 and x0 plus the integral from 0 to t of this expression over here, alpha minus beta f of u and xu du. And so this is, if you wish, this is df dt dt, right? So something like that. So this is df dt, alpha minus beta f with a running index u, xu, du. And then here comes the first derivative, df dx dx. So that is then the integral from 0 to t sigma e to the power minus beta u dxu. And if we write this out, this is just as r0. This is the integral from 0 to t alpha minus beta f of u and xu du. And here we replace x, right? We replace x by e to the power beta u dwu. So this is the integral from 0 to t sigma times e to the power minus beta u e to the beta u dwu. These two together, they are 1, so they cancel out. This f here, that f here, that's nothing but r, that's ru, right? And what remains is exactly what we were looking for. So we see that here we say rt is equal to r0 plus the integral from 0 to t alpha minus beta ru du plus the integral from 0 to t sigma dwu. Now, if we go back, that is our equation 1. So if we go back to our equation 1 in the beginning of this, that is in fact exactly the one that we have recovered. RT is R0 plus the integral from 0 to t alpha minus beta RU du plus the integral from 0 to t sigma du. So we started with 2. We did the Ito-Dublin formula. We chose a particular function of f. We chose a particular xt. We looked at the first derivative with respect to time, the first derivative with respect to space, the second derivative. We applied Ito-Dublin's formula and we ended up with equation 1. Starting with equation 2, rewriting it, ending up with equation 1. So indeed, our equation 2, RT, is equal to e to the power minus beta t r0 plus alpha over beta 1 minus e to the power minus beta t plus sigma e to the power minus beta t, the integral from 0 to t e to the power beta s dws, our equation 2, is indeed shown by the Ito-Dublin formula, is indeed a solution to 1. Now, in fact, we know we can determine the distribution of R. So we know a lot about these processes. So if we make it a little bit more abstract, we can see R as some time-dependent function, we call it little a, plus bt, another time-dependent function, times x, with a and b non-random. So these are deterministic quantities, deterministic functions only depending on time, and x being a normal distribution with mean 0 and the variance, the integral from 0 to t e to the power 2 beta s ds. Again, let's look at R and see if we can indeed see it like this. So R is, here we have this function of t, function only depending on t, little a, and here we have our b, little b, and here we have our deterministic function e to the power beta s, and the Ito integral with respect to of course, the Brownian increment. So that is how we see it in an abstract way. RT is that time-dependent function plus beta b of t times xt, where x is normally distributed with mean 0, and this variance that we can of course also determine, right? This is something that is not too difficult for us. And so here we write it out in detail. Little a t is this first part, e to the power minus beta t, r0 plus alpha over beta 1 minus e to the power minus beta t, and little bt, that is the term in front of the x, sigma times e to the power minus beta t. Now remember that R then is in fact a normal distribution. So if we have R written like this, then it is a normal distribution, because this is just a deterministic function of time. This one is normally distributed. It is shifted, if you wish, and it is scaled. So R is a normal distribution. It has mean AT, because X has mean 0. It has mean AT, and it has variance, the variance of X, times BT squared, right? So it is BT squared times the variance of X. So if we write that out, then we see that RT is normally distributed with mean this part over here, mean this part over here, and with this part being b squared, sigma squared e to the power minus 2 beta t, times that integral here that we can simply compute, 1 over 2 beta e to the power 2 beta t minus 1. So we know a lot about this process. In fact, we know everything. We know a bit more about this process. One thing we know is that it is normally distributed, R is normally distributed, and it can take negative values. Well, in former times, that was a problem, right? Interest rate could not be negative. And therefore, this was used to be named as an undesirable property, right? But nowadays, interest rates can go negative. So if you own a lot of money, then you have to pay instead of getting money. So interest rate is in fact negative. So therefore, the fact that this R process, the Vasicek interest rate process, enables negative values is not an undesirable property anymore, right? In the new regime, the regime with negative interest rates since 2011, something like that, we have negative interest rates. It is not considered to be an undesirable property. It's even a favorable property. Well, the other thing is that we can say something, we see a mechanism in this process, which is also an economic mechanism. Yeah, and that is the mean reverting property. So what does that mean? Well, it means that there is a mechanism mathematically modeled in this SDE, which we also observe in practice. First of all, if RT is equal to alpha over beta, then the dt term is equal to 0. You see that. And now what we see is that when RT is larger than alpha over beta, when it's larger than alpha over beta, then this dt term is less than 0. Yeah. So the change in time is pulling it downwards. Yeah, it's when R is larger than some mean reversion rate, alpha over beta, when it's larger, it's pulled back. The dt term is negative. It's pulled back to its mean. And when RT is greater, is less than alpha over beta, when it's less than alpha over beta, then we see that the dt term is positive. So when the interest rate is lower than its mean reversion rate, its mean average rate, then it's pulled upwards. It's pulled upwards. dt term is bigger, so it's pulled back to its mean. Yeah, and that is called a mean reverting term. And we also see that in historical performances of interest rates in practice. When the interest rate is low, there are mechanisms in the market that make the interest rate go up. When it's high, there are powers in the market that make it go down up to a mean reversion level. Well, this concludes the lecture for now. I thank you for your attention and see you in the next one.